My name is Oreste Fecarotta, and I come from University of Naples, Federico II, the same as Armando Carravetta. Our research group on this work package, that is the work package 6 of the REDAWN project, was led by Armando Carravetta and also Maria Cristina Morani, a young researcher of our group, gave a great contribution to our studies. This is the structure of my presentation. I will speak a bit about the energy potential in water networks, even if you got some information in the previous presentations. Then I will talk about the characterization of the energy source in water networks that has some peculiarities. And then I will do a short list of the possible use of energy and all the available technologies. And then I will focus on the design of the plant. That is the main topic of this presentation. So this will be the main part of the presentation. Then I will present you the design tools of that we developed. They are two computer applications. And then just a bit of information about the location strategy of, we developed some models to perform an optimal location of the turbines within the network. Well, which is the energy potential in water systems? As you know, the water systems can be, for drinking use, of course, can be divided in two parts. The water transmission system from the spring to the tanks and the reservoirs that feed the water network, and the water distribution network that is composed by a lot of branches that are interconnected by each. And then there are a lot of dissipation during the path of water, because they are needed, because for the sake of reducing the leakage of the network. You know, the amount of leakage or water leakage in water distribution and water transmission network is very high. Here we have the percentage, the average percentage of leakage in the European countries. You can see that the amount of leakage can be very high. That's why we need to reduce pressure in order to reduce the amount of leakage. In water distribution network, the reduction of pressure, of course, in water system, the reduction of pressure constitutes a reduction of energy, and this dissipation can be converted into energy. But in water distribution network, the energy source is much variable because of the user's demand that is, of course, variable. And then all this energy is spread on in different different dissipation spots. So we have a great amount of energy that is spread in many spots of low power. So this is, for example, this is just an example of a water distribution network, a water distribution, well, a production point, a possible production point along a water distribution network. In the top right picture, you can see the variability of the flow. In the bottom right picture, you can see the distribution of the head jump, while here you can see the duration curve of the power. The average power is not so low, but you can see that the variability is very high, so it can be difficult to deal with it. That's why we have to think about different possible use of energy. We can have the production with grid connection. Well, I mean, all the production points are inserted in the electric grid, that is fed by several different sources. And here you can see with the name PAT, that is pump as turbine, that is just one of the available technology to produce energy in water networks. They are connected to the network, to the electric grid directly to sell the energy produced to the energy grid. Or we can think about standalone use, which means that the production point can be in remote part of the electric grid, as in this example, or can be totally disconnected. We can think to delete this link, and we can use the hydropower to feed remote areas with energy, with local produced energy. We can use hydropower when the power is very low, much variable, even to control and monitor the water network itself. I mean, we can use a small amount of energy to feed, for example, discharge meters or pressure meters, or to control valves or any device in the water network. We can think about also not to convert the energy into electricity, but to use the hydro energy as mechanical energy to feed another fresh water or a wastewater stream with a specific device. In the future slide, in the next slides, we will talk about a specific device that is a turbo compressor to use directly the hydropower energy to convert into mechanical energy, and then hydraulic energy again. I will talk about this in the next slides. We can think, of course, of about hydropower also to rethink the way we can design networks. For example, as we design a water distribution network, we have mainly two solutions. The first one is to pump power from the source to an elevated tank, and then this elevated tank will constitute the upper head level of the network. And then from this elevated tank, we can feed all the network, and usually we have an excess energy that is merely dissipated by a valve. Or we can directly feed the network with a variable pump. Well, in the first case, we have a backup of water, because this upper reservoir will constitute a backup of water. In the second case, we save energy, of course. Well, a compromise between these two solutions can be to pump water up to the reservoir and then use a PAT, or what else, a turbine, to recover the amount of energy in the case we don't need it. Anyway, we saw the possible use of energy, and now I will list very shortly the available technologies that we can use. This is just a short list. Of course, we have more of them, but we try to collect all the feasible solutions. Well, of course, we have traditional turbines like Francis, Pelton, Banki, and so on. We can use in different cases. We have, of course, the best turbine for each case. They have a very high efficiency and they have high possibility of regulation. But of course, they are the best solution only when the available power is very high due to their large costs. So in water distribution, as I told before, we have low power. So we have different technologies to deal with these low power situations. I divided into low power high production and low power low production devices, which means high production means that we can use this energy for different purposes. I mean, sell energy or use energy to activate other machines and so on. When I speak about low energy, I mean we use the energy just to control the network with some devices. I will talk about this in the next slides. Anyway, which are the available technologies for the high production points? The first one is the PAT, the pump as turbine, that is just a pump that is operated in reverse mode. Of course, they are low-cost device. They have a great availability on the market. They need low maintenance, but they has also disadvantages, such as we need large casing for the piping because they have no control systems, and they have low efficiency, and much more, we have little information about their behavior because pump producers do not furnish the information about the turbine behavior of their machines. We try to overcome this gap, this lack of information in our project. I will talk about this. We have other technologies that are specifically designed. I will go fast on them. We have lucid pipe, that is a prototype. It is under patent. Then its advantage is that we have inline displacement, so we have not much large casing, but we have high cost to install this device. We have some other specific turbines like Saint-Gobain PAM or pressurized Banky-Mitchell. This one, the pressurized Banky-Mitchell, is a very high efficiency turbine. Or we have a tubular propeller. All these turbines are TRL 4 or maybe a little more, which means that they are not fully industrialized and they can cost a lot. They are less more than prototypes. We have also picocentrifugal turbine, which is a specific turbine that has been tested in our project also by the team of Elena Ramos at IST. And then we have the energy booster. That is a specific booster with 2 PET inserted. I will show this in detail a little bit later. Basically, there are 2 submersible pumps placed in a pressurized pipe together with a bypass, and these allow a little regulation of the network and of the system. Then we have the low production devices that are intended to produce a little amount of energy just to operate itself or operate little control of the network. We have the Picogen turbine, the green valve, or some other Pico turbine that produce a little amount of energy just to regulate, to activate valves or to activate meters, flow meters, pressure meters, and so on. Then we have turbo compressors. The first one is the recently proposed PAT pump turbocharger, which is a specific device I talked before in the slide before, where a PAT is directly connected to a pump without any generator. So the hydraulic power that is recovered by the PAT is transmitted by the shaft to the pump to pump water in another circuit. And then we have pressure exchanger that are very high efficiency devices that are used in, for example, in desalination plants, but they are very, very expensive. They are high efficiency, almost as 90% or more, but they are very expensive. So their use in water distribution can be not so viable. Well, I drink a bit of water. If you have any question, please do not hesitate. Okay, let's go in depth with the design of the plant. I will talk about the variable operating strategy, that is the design tools we developed to optimize the optimization of a PET plant. Then I will talk a bit about the design of a turbocharger that can be very difficult, and the design of alternative layouts. For example, a series parallel circuit. I showed you an example before with an energy booster, but I will talk about it in the next slides. Anyway, let's see the variable operating strategy. I told you about the high variability of hydraulic characteristic of a hydropower plant in water distribution networks. Here you can see an example of a highly variable head jump and discharge, as well as high variable power. And then we have to face this variability in an energy production plant. As you can see here on the right side, we put a path along the main stream of water, but a path itself has no regulation devices. So the path is placed in series with a valve. Another valve is placed as a bypass valve, and a specific electric device, I call it inverter or speed driver, is also used to regulate the system. Well, all these devices can be present or not. For example, we have a first example where only the two valves are present. This configuration is called hydraulic regulation system, or HR. And as you can see, all these points represent the different condition of the network. So the available head jump and the available discharge, while this continuous line is the characteristic line of the path of the turbine, rotating at a constant speed. Well, when the available head jump is higher than the one that can be turbined for a specific value of discharge, the series valve operates to reduce the pressure, the excess pressure. When as the discharge is higher than the one that can be turbined with this available head jump, the bypass is opened to bypass a part of the discharge. So any operating point can be translated to the characteristic curve of the path. In the other case, with the electric regulation, the operating points are not moved on the discharge head plane, but the rotating speed of the turbine is modified in order to match the operating condition. I mean, as the rotating speed of the turbine is changed, the characteristic curve of the turbine moves on the QH chart, and characteristic curves is moved in order to match the operating condition of the network. In the third case, where every one of the proposed device is present, we can modify the rotating speed of the turbine, or we can create an additional head drop or bypass to consider the best efficiency condition. Well, all these strategies are used to design a plant, and the best machine can be selected. I will show you later how to do that. To do this, can be selected to operate either in HER or ER or HR mode, which means electric regulation, hydraulic regulation, or hydraulic and electric regulation. So the variable operating strategy is basically a strategy that allows us to select the best machine that ensure the best efficiency or the best reliability or the best effectiveness of the plant. As you can see in this scheme, in this small scheme, of course, the more the possibility of the regulation, the more is the efficiency of the plant. While, for example, in the case of electric regulation, the regulation is simpler and probably the plant is the cheapest one, but of course the efficiency is the lowest one. Then what about the turbocharger? As I told you before, the turbocharger is a specific device that allows the connection between a pat and the pump to use the turbine energy to feed the pump. In this scheme, you can see that the energy of a freshwater stream is used to pump water from a lower reservoir to an upper reservoir. And the equations that regulate the system, these are the equations that regulate the system. You can see, as you can see, the rotating speed that whose symbol is n is not fixed, but depends on the conditions of the system itself. So if the system is closed, I mean, if we have the already designed plant, we knows the performance of the turbine and of the pat, the system is closed and we have 7 equations and 7 unknowns. So once the plant is designed, the resolution of the system can be difficult because it's not linear, but anyway, it's simple. So as you can see here, we can have different working conditions. This is basically the ratio between the discharge of the pump and the discharge of the turbine, and the head of the pump and the head of the turbine for 5 different turbines. And this is the global efficiency of the plant. So basically, these results tell us that the lowest the pumped discharge, the highest the pumping head. But using these equations as design tools, I mean, to choose the right pump and the right turbine to be coupled to design a turbocharger to be inserted in a network can be very difficult. In this case, the unknowns are these coefficients that are basically the performance of the pump and the performance of the pads. And this can be very difficult because the pump manufacturers do not provide these coefficients. And if you can recover them easily for a pump, it can be a very hard work for a pump working in turbine mode. Here you can see the same turbocharger used in a wastewater stream, not in a freshwater stream. I mean, the available energy in the freshwater network is used to feed the pump, to pump wastewater from a lower tank to a treatment plant or what else. And here you can see that we use the same equation of before to predict the pumped discharge, the pumping head, and the power we use to do that. And as you can see, the difficulty is that the available power is always variable because we are using the available power in the water distribution network is of course variable. So the pumping discharge and pumping head are variable in turn. And then finally we have a last scheme that I'm presenting you, that is a series parallel circuit. This is a very simple scheme if we compare this with HR or ER modes and so on, because here we have 2 pads, 2 pump-S turbines that are placed in a specific circuit where these valves are very simple on-off valves They can be open or closed and stop. And this particular circuit is used to place the valve either in series or in parallel, or to close one path and use just one. And as you can see, this allows a sort of regulation. I mean, these are intended to be the operating point of the network. While we can operate on the discharge, we cannot operate on the head, of course. With two series paths, we have the highest head drop, and then we operate with a single path or with two parallel paths, we can increase the discharge that we can deal with. Then we developed some design tools to computer application. The first one is used to retrieve the available data on pump as turbines that are not available. So this database is very precious because it allows to download a lot of information about the working condition of pumps in reverse mode. And another application is just the application of VOS, variable operating strategy, in HR mode, hydraulic regulation. I mean, if we have the operating point of a pressure reducing station, the application tries to find the best machines in order to produce the highest amount of energy. I will show you these two applications running on my computer. The first one is this one. If you click on, they will be available on the REDAWN website. If you click on PAT curves, for example, we have a window with a lot of PAT curves. And if we click just on one of them or just a name, for example, we retrieve information of one of them, and then we can export the data of behavior of one of them on our computer, for example, on the desktop here. And it is a simple text file with all the information we retrieved on the reverse mode of pump as turbines. The second application is the application of variable operating strategy. Here we can add the duration curve of the available discharge and head in the pressure reducing strategy, the pressure reducing point, or we can get data from a specific text file, for example, this one. Then you can see the available points, discharge and the head, the duration curve of the discharge, of the head, and of the power. Then we can launch the variable operating strategy, and the computer tries to calculate the available power for all the machines of the database. For example, here, for these machines, we have 150 kilowatt of production that are compared with 405 available. And if you click on this, you can see the operating points and the head curve of the turbine. Of course, you can see that most of the points are bypassed. And if you click on another curve, on another bar, you can get different information about another machine, for example, this one. And you can see also the efficiency of the machine when operates with different points. Well, let's go back to the presentation just to end it, because the last, sorry. Okay.
Sorry, Oreste, I have a question.
Yeah.
This design tool is available on the website?
Yes, of course. Of course, okay. It will be available on the website as well.
Okay.
Together with a brief description and instruction on how to use it.
Oh, yeah.
Okay. Just the last topic is a brief introduction to the location of the turbines within a distribution network that is a very complex problem. Sorry, yes, we have just 1 minute.
Be careful with the time, Oreste.
Yeah, because
they are trying to close our
just to tell you that this problem can be very complex because the turbine influence the way that the network behaves and vice versa. So basically, this is a very complex problem. These are all the equations for a simple network. We have thousands of them. That's all, folks. We have few seconds, maybe 20 seconds. These are our emails, our contacts. If you have any question, you can write us or what else. Thank you very much.
I will have some question because
we have 7 seconds. Sorry.